thank you for the introduction. Yes, I'm Gianfelice Cinque from Diamond Light Source, and I'm going to present a bit of a mixed bag. It's not going to be scattering s-SNOM only, it's going to be also photothermal, because traditionally we started with photothermal, and in the last 5 years we spent more time on that. So everybody is showing a nice picture of his own synchrotron. This is our night view of Diamond. When it's not raining, it's quite nice. And the outline of the talk is the following. So I'm going to talk about Diamond and the beamline as a background, so you can think in terms of where. The synchrotron IR motivation has been said several times, and the nanoIR rationale, which means why and how. And the new instrumented first performances, which are the very first, so they are a bit crude data. And the future development of what's next. So Diamond Light Source is in the south of Oxfordshire, south of England, Oxfordshire, half an hour south of Oxford itself, is the UK national facility, but of course we are still taking a lot of international users, including the European community, of course, and this is a large fraction, this is 30% of our users. So there are many parameters in a synchrotron which matters, but I'm not going to bother you with many, apart from the energy there. The fact is a relatively large circumference. This part of the source doesn't matter because we are geometrically limited, even if diffraction limited when it comes to the focus. There were some questions about the time resolution. Well, remember that the time is, we use it as a continuous source, but it's not. We have a 20 picosecond full width maximum bunch, and it's separated 2 nanoseconds. So in principle, there is a lot of studies that can be done with time resolved. The other two important parameters worth considering is the top up every 10 minutes, which means that essentially you don't have to bother about the normalization of the spectra. The variation of the intensity in the photons is less than 1%. And the fast orbit feedback, so any vibration below 100 Hertz is compensated. So the beamline itself, in a nutshell, is the following. So you have a source there, which is the green bending magnet. And then you have these optical system, 2 periscopes. We are focusing the radiation midpoint, and we're bringing the radiation to the 2 endstation, which are obviously named upstream and downstream. So this scale is quite misleading because this is 26 meters, roughly speaking. It's a quite neat setup, and it works quite well. And in practice, what the users see is the following. So this is the upstream endstation, and this is the downstream with a new instrument there. And we dedicate the first one, the upstream, for micro FTIR, FTIR and TeraHertz in the bench there, while the downstream we have the micro FTIR scanning mode, the FPA imaging, and of course the new nanoIR. Right. So in terms of application, because we are a user facility, of course we always confront ourselves what are the users' demand. We had the lab review about a few weeks ago, and what it came out in this pictorial view is that we are dominated by biochemistry. And biomedicine is also going across biochemistry and chemistry itself, because of the reason of some classification of the publications. So chemistry for us means catalysis, in situ, temperature-controlled, gas-controlled reaction. Biomedicine, we still try to push a lot about living cells, which is where we have an edge. Material science engineering is more related to the sample environment. For example, this is coming from graphene oxide stress and strain test under the microscope. In physics and chemical engineering, there is a lot of emphasis on terahertz these days, especially on MOFs material. And I think the latest novelty is the capability of measuring the electric functions, real and imaginary part, in one place, going across from the near infrared to the far infrared. And of course, a lot of interdisciplinary, which means paleontology, astrobiology, and cultural heritage. Right, so the motivation, I borrow this image again from Hans and company because it's quite neat. And of course, it's showing what the synchrotron, in this case ALS, is doing compared to a black body in terms of spectral irradiance, which is the power per unit area, per unit bandwidth. And of course, this is the diffraction limit in comparison with some lasers. Of course, laser technology is improving, but it's clear that the bandwidth of a synchrotron is quite remarkable. In our case, of course, the comparison is slightly different. We use a different temperature of the black body, but it doesn't matter too much. The diffraction limit is the dotted line you go there. And I think it's important to emphasize that the use of the edge radiation, for example, in our case, which we use a lot, is enhancing a bit the flux in the terahertz region. So it's quite unique to use 3 decades of bandwidth, which is something that the laser cannot do yet, at least. Right. So the motivation, again, everybody is showing this graph, and this is our personal graph of what we were doing since 2016, which is the photothermal. It looks like an exercise of spot the difference, but it's really very different. Because, yes, the common part is we have a synchrotron in both cases, we have an interferometer, and we have a tip. But in one case, you have an asymmetric interferometer and a detector. In our case, it's symmetric, plus you have a fast chopper. Right, so there is quite so complementary, and that's, I think, the point I'm trying to make here, in order to use both technologies for different applications. So the resolution of the scattering system is quite strong. Definitely, you can go below 100 nanometers in terms of synchrotron. The spatial resolution, the photothermal, typically is not that strong. We use it above 100 nanometers. But there is the advantage of bulk sensitivity. You can measure samples which are well beyond 100 nanometers. We can measure samples of a few microns as well. We are not surface sensitive, of course, while the scattering SNOM is extremely surface sensitive. There is always a signal with the scattering SNOM, and the question is sometimes if it is a good signal and what this means. While in this case, when you don't have an absorption and you don't have a thermal expansion, you're not aligned, you don't have a signal. But it means that when you have, it is intrinsically a true absorption signal. And the last point is that, of course, depending on the spectral range you want to use, you need the right detector, for example, the terahertz. While in this method, you don't need the detector, so the tip itself is your detector. So there are quite some complementarity. So if you were coming to the Beamline until the summer last year, assuming the lockdown was allowing to come, of course, you could have seen this kind of setup. This is our microscope, and this is our Beamline, developing with the source down there. So this is our microscope and the control unit with the lock-in there. So what we were trying to prove was that we can measure, for example, material that has got absorption and thermal expansions. Polymers are the classic example. So again, this is spot the difference between which one is the far field, which one is the near field spectra. And actually, the bottom one is the near field because you can go lower wave number. The top one is the far field because we had a cutoff of the window. A more meaningful scientific application is the one of looking at macrophage cells and phospholipidosis induced by drugs. So you can do a line scan, you can measure the topography or the signal, the amide one, or you can look at the spectrum across this line and see the variations. That's exactly what we were achieving until last year. Right, so the new instrument that is on the Beamline nowadays. So we installed this in October. The Synchrotron beam is coming from here. And this is some optics, which is just complicating our life for the time being. We intercept the beam here. We bring it to these positions here. So we bypass the interferometer of the microscope. And we have a switch mirror there that can either switch the radiation through the chopper or can go through the scattering SNOM. Now, I don't need to explain here the head of the AFM system, the near-spec system. And this is our chopper. It's a very small object, but it's quite useful. We have to focus the beam and bring it back to collimated. The real advantage of having an in-vacuum ultra-fast chopper is that you can go up to 200 kilohertz with a very low jitter. And this was an upgrade done before the installation. And here I show the photothermal signal of chanacrylate, first harmonic and second harmonic. And the second harmonic, you have quite an enhancement of the signal to noise, which is exactly what we were expecting. So there is an advantage there. The coupling optics is the following. So you see, this is a double image. We have the green laser beam, which is the pilot laser, tracing back to the asymmetric interferometer, sorry, symmetric interferometer. And this is the synchrotron beam coming outside the chopper box and coming there. So this is how we align the system in order to be sure that the optical alignment is given the maximum signal. And of course, we complement with QCL laser because of the user request of nanoimaging. So we take a leap of faith and had users in November after the installation in October. This is an example from collaborators of the Natural History Museum of London, and they want to study the origin of life in asteroids, and particularly chondrite, and look at the organic phase in there, because the standard method of digesting an acid solution practically cannot dissolve the crystals where the organic matter is supposed to be. So the crystals are less than 1 micron, so ideal for this kind of study. So this is just an image with his EDX showing magnesium, iron, and silicon. So you can see the crystal structure that we are interested in. This is the really cut and paste image from the Near-spec system that shows that there are quite some interesting signals there, which are the silicates. So that was interesting because this is the hydrated silicon oxygen in the silicon mineral from these 4.6 billion years old asteroids, which has been altered by the H2 by water. And of course, we were interested in looking at these hotspots. When we were trying to look at these hotspots, we realized that the signal was stronger than our background, and in fact, this is the metal. So there are metal inclusions, and of course, we were expecting that, but it's always come as a change in the science there. So the more recent example is this one from Maria Paula Marquez from Coimbra University. So osteosarcoma in this case, actually, the study. And the idea is to study non-conventional platinum and palladium-based drugs versus cisplatin, which is quite well known and quite well studied. So the idea was, let's try this. Let's see if there is any difference with respect to osteocyte or osteoblast wild type. So the first question was, can we actually compare the far field with the near field? And you can see that the comparison with the band assignment is quite good. And it's also showing that we can actually see better the low wave number region, which is interesting and is quite useful because if you want to look at the phosphate groups and the effect of the drug on the DNA, that's exactly where you want to focus on. The counterpart is, of course, that we cannot look yet at the stretching region yet. And that has been always the most challenging aspect in this kind of study. Right. Future developments. I haven't talked much about the photothermal as it is. But of course, I need to talk about the TeraHertz because this is a research field which everybody's interested, us in particular. And so again, I nicked these two slides, these two images from Hans, Mike, and Larry paper. And of course, there are many interesting molecular or quantum excitation. For us, the interest is in this multidisciplinary and MOFs kind of application, because that's where you can really go to the application that which is closer to our user community. And of course, everybody's interested in these detectors, which are overlapping nicely with the MCT. The technology of these detectors is relatively simple, but the actual chip is quite precious. So we recovered one chip, which is enough to make a detector. So we're starting from scratch in this sense, and we're going to rebuild the detector looking at the example of our colleague at Berkeley and Brookhaven. So I have to thank the people on the Beamline, especially Mark and Yanis, a lot of scientists and engineers that help us control Ed, Andy, Paul, Kieran, Alessandro, Steve, Eugene, Timon and Martin from Synchrotron, Felix, Adrian, Florian, and Ivan. So this is the Beamline as it is nowadays. And this is the installation at the end of the October, when, of course, everybody was having this masquerade kind of approach. I'm going to conclude just before saying thank you to everybody for the attention, highlighting that we have an open position, a full permanent position, for an experienced scientist that wants to work on the nanoIR, both the scattering and the photothermal. And with this, thank you very much.